All right, so let's get started. Okay, so last week we briefly mentioned the maximum weighted matching problem. Okay, so we haven't discussed the algorithm. So today our first mission is to consider the algorithm for maximum weighted matching. Okay, so let's first review the definition. Okay, so in this problem, again you want to find a matching, but now these edges have weight. Okay, and you want to find the matching that has the highest total weight. Okay, and once again we only consider bipolar graphs. Okay, so for general graphs, the problem is still polynomial time solvable. Okay, but we're not going to mention the algorithm here. Okay, so we just focus on bipolar graphs. Okay. Okay, so we're going to use W to denote the edge weight. Okay, so for example, in this simple bipolar graph, if you choose these two edges, then this will give you the maximum weighted matching with a total weight of 5. Okay. Okay, so we have two assumptions that make our discussion easier. Okay, so the first one is that the bipolar graph will be balanced, which means the two sets x and y they'll have the same size. Okay, and then we're going to add all the possible edges between these two sets so that this will give you a complete bipolar graph. Okay. So the reason I want to use these two assumptions is that we're going to have a perfect matching as the maximum weighted matching. Okay, so the best matching must be perfect. Okay, all right. So these are the two assumptions that we need, and just like the unweighted matching problem, where we just want to maximize the number of edges, we consider an upper bound. So the upper bound is the size of any vertex cover. Okay. So here we generalize the idea of vertex cover, but since now edges have weight, so in our vertex cover, vertex also have weights. Okay, and to cover an edge, okay, so for example, to cover this edge between A and D, we need to assign weights to A and D. Okay, so we're going to assign vertex weight so that the total weight of the endpoints is at least the edge weight. Okay, so this is how we cover an edge, by assigning sufficiently large weight to the two endpoints, so that the total weight of the endpoints is at least the edge weight. Okay. All right. So last week we showed that if you have a weighted vertex cover, then the total weight of the weighted vertex cover is an upper bound for the maximum weighted matching. Okay. So for example, in this case, we assign this 2400 as the vertex weights, and the total weight will be 6. Okay, and the best matching the best matching has a weight of 5. Okay, so 6 is greater than 5. Okay, so indeed this is an upper bound. Okay. Okay, so let's briefly review the proof. Okay, so first consider the total weight of the matching. Okay, here we just consider all the edges in the matching M, and we sum up their edge weight. Okay, so this is simply the total weight of the matching. Okay, and for this inequality, we use. This is the claim. Okay, and this is the proof. Okay, so this is the total edge weight of the matching, and for this inequality we use the definition of weighted vertex cover. Okay, because it is a weighted vertex cover, so as I mentioned earlier, the two endpoints, their total weight must exceed or at least equal to the edge weight. So we have this less than or equal sign here. And then for this equality, we use the definition that the matching is perfect, okay? So here we only consider perfect matching here, okay? So if we only consider perfect matching, then in this summation, we consider all the vertices in the graph because this M is perfect. So we can consider all the vertices in this summation. Therefore, we have this, the final equality, okay? Okay, so I think for this proof, the most critical part is this inequality, where we relate the edge weight to the vertex weight, okay? So if this becomes an equal sign, then these two summations will be equal, okay? So we'll give this spatial edge, we'll call them the tight edges, okay? So an edge is tight if the sum of the two vertex weight equals the edge weight, okay? So this is when we call this edge tight. Okay. So today our goal is to find a perfect matching, okay? And we also need to find a weighted vertex cover C so that every edge in this perfect matching is tight, okay? Then according to our previous proof, this one, okay? According to our proof, we can show that the total weight of the matching equals the total weight of the weighted vertex cover, which implies that the matching is the best, okay? All right, so yeah, we want to find a perfect matching, and we want to make sure that every edge is tight. Okay. All right, so this is our first goal today. 我不知道大家有没有问题，所以我们今天要做的事情，第一件事情就要找bipartite graph， 然后是 edge 有 weight 的bipartite graph 上面的 perfect matching，OK。然后我们为了要确保说我们找到的是最好的，就是 maximum weight 的 matching， 我们会需要再另外找一个 weighted vertex cover， 然后确保说这个 weighted vertex cover 可以让这个我们找到的 matching 上面的每一个边都是 tight，OK。tight 的意思就是刚刚我说的，就是两个 endpoint 它们的 vertex weight 的总和刚好会等于 edge weight， 那这个时候这个 edge 就会是 tight，OK。Okay, so so in this algorithm, we're going to maintain not just the matching. Okay, we also need to maintain the weighted vertex cover. Okay. So first we're going to compute a weighted vertex cover C, okay? So this is our first step, okay? And then we're going to find all the tight edges. Okay? And after we find all the tight edges, we're going to try to find a perfect matching using just these tight edges, okay? But how to find perfect matching using just tight edges? So we actually we're going to find the maximum matching, okay? By maximum matching, I mean the matching that has the most edges, okay? And again, using just tight edges, okay? So to make this idea formal, so let's consider another graph. Let's call this graph GT, okay? So T stands for tight, okay? Okay, so we just use these tight edges to construct a graph. Let's call it GT, okay? And then we try to find a maximum matching on GT. Okay. Right, and we just check, okay, so if M is indeed perfect, that means we have found a perfect matching, and all of its edges in M, this maximum matching, are tight, okay, which implies that M is the best. M is the maximum weighted matching. Okay, so this is like the good case, but when this M is not perfect, then we need to modify this weighted vertex cover, right? So that we can have more tight edges. So if M is perfect, we just output M. Otherwise, we need to update this weighted vertex cover C and just repeat this process in the hope to have more tight edges, which will enable us to find a perfect matching. Okay, so this is like the general steps for this algorithm. Okay, we start from a vertex cover C, find all the tight edges, see if the maximum matching is perfect. Okay, if so, then we're done. If not, we need to modify the vertex cover. Okay, so let's first consider this first step. Okay, we need to have a weighted vertex cover, and this really is any weighted vertex cover. Okay, all you have to do is to like satisfy the constraints for weighted vertex cover. Okay. So let's consider the following example. And also, because next we're going to consider complete bipartite graphs. So you can see that there are lots of edges here, and it's not easy to put numbers along with these edges. So we're going to consider the matrix representation, okay? So let me first give you perhaps a smaller example. Okay, like this one. Okay. So this is our like normal representation for a weighted bipartite graph. Okay, we just put numbers alongside these edges. But next we're going to consider a more compact way of doing this. So we're going to just write this as as this matrix. Okay, so these entries are just the edge weight. Okay, So for example, the entry for x1, y1 will be 2. This will be the edge weight between x1 and y1, okay? And the entry for x1, y2 will be 3, which is just the edge weight between x1 and y2, okay? So different rows correspond to different vertices in X, and different columns refer to different vertices in Y. Okay? So we have this matrix. Okay, so next we're going to just consider this matrix form for weighted bipolar graphs. Okay. So for this example, let's first try to find a weighted vertex cover, okay? So we need to cover all these 4 edge weights, 2, 3, 1, 4, by assigning numbers or weights to the vertices, okay? So I think one way to do this is that let's just assign zeros to y, okay? And then let's figure out what should be the numbers for x, okay, to cover all the edges. So for x1, we need to cover this edge weight of 2 and 3. So the number or the weight for x1 should be at least 3, okay? And in fact, we should not use any number greater than 3 because, for example, if we use 4, then we cannot have any tight edges. Okay, so the only reasonable design or the only reasonable weight for x1 will be 3. Okay, so that we can create at least one tight edge. Okay, similarly for x2, the number or the weight for x2 should be at least 4, so that it satisfies the constraint for weighted vertex cover. Okay, but we should not use any number that is greater than 4 because otherwise, we cannot create any tight edges. So the only reasonable number for this x2 is 4. Okay? So this just finishes the first step. Okay? We have created a weighted vertex cover C. Okay? And the second step is easy. Okay? We just find out all the tight edges, okay? So we have, this one and this one, okay? All right, so these are our 2 tight edges. Okay. All right, and then let's construct this GT, okay? Let's call it tight graph, okay? Okay, because all these edges are tight, okay? Okay, so we have a tight edge between x1 and y2, and a tight edge between x2 and y2. Okay, so that's our tight edge. Okay, so this is GT, the tight graph. Okay, and then we need to find a maximum matching. Okay, so we can use the previous algorithm where we have a maximal matching in the beginning, and then we try to find augmenting path. To find augmenting path, you need to gradually expand this S and T until you find an unsaturated vertex in T, and so on, okay? So we just keep finding augmenting path, okay? Anyway, here you can think of any black box algorithm for maximum matching algorithm, okay? Okay, so for this one, it's easy to see that for the maximum matching, we can have at most one edge, okay? Okay, so then we have to check whether it is a perfect matching or not. So clearly, this is not a perfect matching, okay? So this means, according to our algorithm, we need to update our vertex cover so that we can have more tight edges, okay? So next we want to add like edges to this tight graph so that we can find the perfect matching, okay? Now to have more edges for this GT, and we want to have a perfect matching, or we want to have a larger matching, a matching that is larger than this, the matching here we have, okay? So to do this, we're going to once again consider augmenting path, okay? Because if you want to have a larger matching, and in some sense you need to have an augmenting path, okay? And to find augmenting path, recall that we have these two sets, S and T. Okay, so let's recall the definition of S and T. So what is S? So S, first of all, it is a subset of X, okay? And initially, it contains all the unsaturated vertices. So in this case, just X2. So X2 is not saturated. So initially, X2 is in S, okay? And then we're going to extend this alternating path, okay? So if we can use alternating path to reach some vertices in X, then that vertex is also in S. So in this case, X1 is also in S because we can use this alternating path to reach S, okay? To reach this X1, sorry. So that's for the part X. For Y, if we can reach it by some alternating path, then by our definition, the vertex will be in T. So in this case, Y2 will be in T. Okay? And that's it. So these are just the previous sets S and T, okay, applying to this graph. Now, why do we consider this S and T? Because if you want to have augmenting path, we should find some edge between S and Y minus T, okay, so that we can extend this alternating path from S to some vertex that we haven't explored before. So the key idea is that we need to create some tight edge between S and Y minus T. If we can create some tight edges between S and Y minus T, then we can extend alternating path and we may find a larger matching, okay? And if we can find a larger matching, then we can just repeat this process until we find a perfect matching, okay? So this is the general principle behind this algorithm. OK， 所以这个蛮重要的，所以这个等一下我们要做的事情就是想办法，当你刚刚的那个 tight graph 上面的 maximum matching 你发现不是 perfect 的时候，你就要想办法让它变大。那你要让它变大，我们这边做的事情就是要想办法让它去长 alternating path，OK？ 那你要怎么让它长 alternating path？ 那我们要做的事情就是，我们一定是从 S 出发 ，OK， 从这些 S 出发 ，S 就是之前有讲过，就是 alternating path 可以经过然后在 X 里面的点，然后想办法去延伸。那它延伸的时候，它一定会想办法走到不在 T 里面 ，OK， 这样它就可以去延伸它的这个 S 跟 T，OK。那比如举例来讲，比如说，你可以把这个 H 就加进去，那这边就会有一个 augmenting path， 你就可以找到一个更大的 matching，OK。所以这就是我们接下来要做的事情 ，OK。好，我到这边我不确定大家有没有什么问题。有问题吗 ？OK， 好 ，All right. So now the question becomes how to create tight edges between S and Y minus T. Okay, and because to have more tight edges, this means we need to modify this vertex weight. Okay, because to create tight edge, you need to make sure that the sum of the two endpoints weight equals the edge weight. Okay, that's how you create a tight edge. Okay, but now we want to make sure that this tight edge is between S and Y minus T. Okay. So how to modify the vertex weight so that we can create a tight edge. At least from this example, we want to create tight edges between x1, x2, and y1. Okay. In other words, we want to make these two edges, or at least one of them, tight. Okay. 所以我们现在目标就是想办法让这个2跟这个1的这个 edge， 我们要去调整上面的这里的 weight， 然后让它们变成 tight。OK。And also we want to make sure that all these edges that we already have between S and T, they are still tight. Okay, so this is also very important. Okay. So otherwise, if you just want to make one of these two edges tight, you can just, for example, assign 2 to x1 and assign y1 0. Then you get this tight edge. Okay, but you do not want to create a whole new vertex cover. You want to create or update this vertex cover based on the vertex cover you already have. Okay, so let's first observe these two edge weight, okay, 2 and 1. So let's first consider x1 and y1. So the edge weight here is 2, and the sum of the two vertex weight, x1 and y1, is 3, okay? So 3 is greater than 2. So to make sure that this is tight, we have to reduce the weight for x1. Okay, so for example, by subtracting 1, then we get 2 and 0, which makes this edge tight. Okay, but also we need to make sure that the original tight edges are still tight. So if we subtract 1 from x1, then we need to add 1 to y2 so that this edge is still tight. Okay? Okay. And you can see that after we add 1 to y2, this edge is no longer tight, okay? So we need to modify the weight here. Okay. So we're going to, again, subtract 1 from x2, okay? So the general idea is to subtract some number from S, okay, and add some number to T. And we just need to figure out what is this value, this number here, epsilon, okay. Okay, so let's try to figure out what is this epsilon, okay? So if epsilon is less than 1, so for example 0.5, so we subtract 0.5 from 3 and 4. And the problem is that we cannot have any tight edge, okay? So 3 minus 0.5 will be 2.5. So 2.5 is not equal to 2, so this is not tight. Similarly, for this one, it is not tight, okay? And if this epsilon is greater than 1, for example, say 2, then 3 minus 2 will be 1. Then this will not be a weighted vertex cover because it cannot cover this edge. Okay, so here epsilon should be exactly 1. So the reason it should be exactly 1 is that if you consider a larger number, then you cannot have a weighted vertex cover. Okay, and if you consider a smaller number, then you cannot have a new tight edge, okay? So it should be exactly just 1, okay? All right, so after we subtract 1 from S and add 1 to T, we have one more tight edge. Okay. And after we have one more tight edge, it's easy to see that we have an augmenting path here, so we can have a larger matching. Okay, and this time this is a perfect matching. Okay. So for this problem, this is our final output. Okay, an edge between x1 and y1, and edge between x2 and y2. Okay, and how to show that this is really the best matching. Okay, so the total weight here is 6. Okay, 2 plus 4, 6. And we also have a weighted vertex cover. So what is this weighted vertex cover? Okay. So 2, 3, 0, 1 will be our vertex cover. Okay, and you can see that the total weight is equal to 6. Okay, and you can check this 2, 3, 0, 1 covers all the edges, okay? So for example, the edge between x1 and y2, well, this one has a weight of 3, and these two vertices have weight 2 and 1. So their sum is equal to 3, okay? Okay. So let's, again, try to formalize the idea we have. Okay. So now you can see that the real problem is how to update the vertex cover C, okay? Okay, so now we're going to consider the details for the 5th step. So after we find this maximum matching M is not perfect, we need to update. Okay, we need to update the vertex cover we have so that we can have more tight edges. Okay. So to update this weighted vertex cover, we first find S and T with respect to the maximum matching M we have. Okay. And then we try to find that epsilon. Okay. We'll try to let me put this. Okay. So we're going to find a magic number epsilon, okay? And for every vertex in this set S, we're going to subtract epsilon from their vertex weight. And for vertices in in T, we're going to add epsilon to their vertex weight, okay? Just like we do here, okay? So for vertices in X, their vertex weight is decreased by epsilon, and for vertex weight or vertex in T, their weight is increased by epsilon. Okay, we just need to figure out the exact value of epsilon. Okay, but after we do this, we can make sure that at least all the edges between S and T, they are still tight, okay? Because for edges between S and T, initially they are tight, okay? Why? Because these are the edges between, these are the edges in GT, okay? And they are between S and T. So if we subtract epsilon here and add epsilon here, then the result is that we do not change the total weight, okay? So if originally we cover this edge, and after this modification, we still cover this edge weight. We still cover this edge, and still the edge is tight. Okay. Now let's consider the epsilon, the value for epsilon. Okay. So the purpose of this is to make sure that some edge between S and Y minus T is tight. Okay, so this means before we change this weighted vertex cover, all these edges between S and Y minus T, they are not tight. If they are not tight, this means the vertex weight is greater than the edge weight, okay? So we need to decrease this vertex weight in S, okay? So we're going to find the smallest gap between the edge weight and the sum of the two endpoints, okay? Or so what do I mean by gap? So gap is just the sum of the two endpoints, or the weight, minus the edge weight, okay? Okay, so for example, all right, so this is our initial weighted vertex cover, 3, 4, 0, and 0, okay? And we want to make at least one of these two edges between x1 and y1 and x2 and y1. We want to make sure that at least one of them is tight, okay? So if you apply this definition of gap, okay? So what is the gap for this edge? So the gap will be 3 plus 0 minus 2. So for this gap, for this edge, the gap is 1. And for this edge, the gap is 4 plus 0 minus 1. So the gap is 3, okay? And we want to find the smallest gap, okay? I think that, for example, if you set epsilon to 3, okay? So y3, 3 is the gap of this edge. And then you can see that there's a problem here, because after you minus 3, for x1, the weight of x1 becomes 0. And y1, the weight is still 0. So we cannot even cover this edge, okay? So we cannot have a larger epsilon, because otherwise we cannot have a weighted vertex cover, okay? So okay, so if epsilon is larger than the minimum gap, then we cannot have a weighted vertex cover. On the other hand, if epsilon is less than the minimum gap, then the problem is that we cannot have a new tight edge. Okay, so epsilon should be exactly equal to this smallest gap between S and Y minus T. Okay. So if you set epsilon to this minimum gap, then we can know that at least we can have one new tight edge. So after we update the weighted vertex cover C, we can add at least one edge to GT, the tight graph. Okay. Okay, and then we can just repeat the process of finding maximum matching and see if the matching is perfect. If not, we'll do this again. OK， 所以到这边有问题吗？我们这边主要要讲的就是，如果今天你发现 maximum matching 不是 perfect 的时候，我们就需要去调整这个 vertex weight。那在调整这个 vertex weight 的时候，它的最主要的精神就是跟之前的 alternating path 是一样，所以我们会想要去找这个 alternating path。你要找 alternating path， 我们的做法就是要想办法去找一些新的 edge， 然后这个 edge 是介于 s 到 y 减 t， 所以我们的整个流程就为了要去新增 tight edge， 我们是必须要去调整 vertex 的 weight，OK？、所以我们的调整方法，第一个是 s 里面的点，它的 weight 要减掉一个数字 ，t 里面的 weight 它的weight 要加一个数字，然后这两个数字是一样的，所以这样的效果就是，当你 s 扣掉一个数字，然后 t 加上那个数字，那其实它们的总和是不变的。所以如果本来是 tight， 它一样继续会是 tight，OK？、所以那个 GT 里面的那些edge 你就可以继续留着。然后所以接下来问题就是你要怎么决定这里的 option，OK？、所以这边的 option 这边的关键就是你要去看，因为我们的目标是要 s 到 y 减 t， 这个里面有一个新的 tight edge。那新的 tight edge 就代表说，过去介于 s 跟 y 减 t 的，它们都不是 tight，OK？、所以就像是刚刚这里的2跟1一样，2这里它不是 tight， 因为这个总和是3； 1这个也不是 tight， 因为它总和是4。所以就代表说你目前的 weight 都有点太大，所以你要扣掉一些数字，扣掉那个 option。那你要扣多少？就是扣看，有点像是这个剩下的多的空间有多少。对这个 edge 来讲，因为它的 weight 是2，然后左右上下的两个 endpoint 3跟0，所以它有一个扩大是1。所以就是我们刚刚那个 gap 就是1，那对于这个 x2 跟 y1 的，它的扩大，它的 gap 就会更大，是3。所以我们就是至少要确保说一个是 tight， 所以我们这个就会选最小的那个 gap， 所以就会让这个 option 设成1，那这样子就可以确保说这一个 edge 它就会变成 tight，OK？、那刚刚我后面还要讲说，如果说我们今天这个 option 不是设成这个最小的 gap， 它可能设成一个比较大的数字。那比较大的数字，它的问题就会是，这可能甚至不是一个 weighted cover， 因为像这个，因为这边的 gap 只剩1了，所以你扣掉一个比1更大的数字，就会让这个 x1、y1 没办法去 cover 这个 edge。OK， 所以这是当你的 option 设太大了，那 option 设太小的问题就是，没错，你一样继续可以是 weighted cover， 但是你就没办法有新的 tight edge。OK。好，所以我们先下课，我们等一下会看一个比较大一点的 example。一模一样的。可是它这边的 epsilon 是要针对某一条特定的 alternating path。这里的 epsilon 是针对 s 特定的 s 跟 t。对啊，就它不是就以前在讲那个 s3t， 但是比如说 s 好了，它就是说 unsaturated point vertices 都会在 s 里面。对，那是一开始，然后我们甚至接下来从那些 unsaturated vertices 我们会去走那个 alternating path。所以，可是在这个情况里面 ，s 不会是所有的 unsaturated， 因为它必须要是那一条 alternating path。对，没错，所以我们之前的定义那有一个 set 叫 U 才会是所有的 unsaturated， 然后一开始 S 有包含 U， 然后 S 会越来越大，因为它就可以从 U 出发，然后走 alternating path。那走到那些点，如果是在 x 里面的，它就会被加到 s。所以像这个 x1， 我们看刚刚这个。OK， 所以如果你是用这个3400这个的话，一开始的 tight edge 只有这两个 ，OK。只有这两个。然后我们刚刚说的事情是，我们就比如说选这个当做 maximum matching， 那这样子的话 x2 就没有被 saturate， 那 x2 没有被 saturate， 所以它就在 U 里面，所以它就一开始在 S， 所以它就可以走这一条，然后再走这一条， 所以这条你也可以，这个 x1 你也可以抵它，所以这个 x1 它也会在 S 里面，所以这个定义跟之前是一样。OK。
所有 S 都会在，就是所有 unsaturated 都会在 S 里面。
哎，没错，对。
那这样不就不合理吗？因为
为什么？
如果所有 unsaturated 都在 S 里面，
对，
那代表说，因为你 alternating 它不一定每一条都会，就你的 S 里面可能会有很多条 alternating
path。S 里面会有很多条 alternating path， 这句话指的是，因为 S 是点的结合嘛。
对。
你是说 S 可以
很多条
对，可以长，没错，可以长出很多条。
每 S 里面每一个点都要减 epsilon， 这样不就怪怪的吗？它不是只针对那条 alternating path 做处理而已吗？就是照你这个推这个逻辑，比如说你之所以在这边全都减，是因为这条 alternating path 加进去之后。
OK， 我了解你的问题。所以你的问题是为什么要每个 S 都要去减 epsilon？
对。
OK，
不是只有那一条。
OK， 那这个原因就是我刚才有讲，maybe 我可以，因为刚好上课，我可以顺便回答大家。对。OK， 因为刚刚下课有同学问我一个问题是，像以刚刚我们回到刚刚那个状态。OK， OK， 所以刚刚一开始我们的weighted verse cover 是3400，那个时候我们会有这两个 tight edge，OK， 那有了这两个 tight edge 之后，我们说我们就会把 x1 跟 x2 都放到 S 里面，那这个中间是因为我们选了这个当做 maximum matching， 然后所以这个没有被 unsaturated， 没有被 saturate， 所以我们可以走 alternating path 抵达这个，所以这个也在 S。然后这个在 T 里面，那如果我们稍微快转一下，快转到后面的结果，后面的结果就是我们会加这个边进去 ，OK， 会让它这个变 tight，OK。那刚刚有一个同学的问题是，乍看之下这样子我们好像只会去影响其中的某一个 alternating path，OK。换句话说，这个起点，因为我们这边刚好是一个 special case， 是只有一个点它没有被 saturate，OK。那这个时候，我们如果马后炮回来看的话，就变成是我们只针对其中一个 S 出发的 alternating path 去调整 ，OK。那这样为什么我们在 S 的每一个点都要去扣掉 epsilon？ 因为很有可能未来有 x3、x4 它们也没有被 saturate， 那这样子根据我们这边说法，它也要减掉 epsilon，OK？ 那为什么它们也要减掉 epsilon？OK？ 那这边的原因基本上就是我们刚刚有稍微也有 cover 到，就是我们一开始只有，如果大家有印象的话，我们一开始只有在 x1 这边有减 epsilon，OK？ 那 x1 这边减了 epsilon 之后，为了要确保说这一个本来的是 tight， 它一样会继续是 tight， 所以这边会加 epsilon。OK， 那所以就我们会 follow 这个逻辑，所以我们本来会是 tight， 我们希望 update 完之后继续是 tight， 所以这样子这个往上的这个 edge 我们也会希望它是 tight， 所以这个 x2 它本来有点像是不算是在我们的考虑范围里面，我们也会就是减 epsilon，OK， 所以简单来讲，就是最后面这里第二步这一步，它如果可以把每一个 S 都扣掉 epsilon， 然后每一个 T 的都加上 epsilon， 这样我就可以确保本来的那些 tight edge 一样会是 tight。那因为我很难去预测说我要用哪一个 alternating path 继续往下涨，所以我会希望那些本来是 tight， 它继续会是 tight。那如果我要确保这件事情，就是所有的 S 跟 T 它都必须要一样继续保持是 tight， 所以 S 每一个 s 的都要减掉，然后每一个 t 的都要加。这样我不知道有没有回答问题 ？OK。Okay, so next let's consider a larger example. Okay. Okay, so this is again a complete biparallel graph where x and y they all have 5 vertices. Okay, so we have 25 edges. So for example, the edge weight between x1 and y3 will be 6. Okay. So the first step, well, we have to create like the initial weighted vertex cover. And for this initial weighted vertex cover, we're going to just assign 0 to the vertices in y. And for each row, because we need to cover all the vertices or all the edge weights for each row. So for example, for the first row, to cover all these 5 numbers, the vertex weight for x1 should be at least 6. In fact, we're going to just use 6, okay? Because any number greater than 6 cannot create tight edges. Okay. So for every row, we just find like the maximum number. So for the second row, the maximum number is 7. And next 8, 6, 8. Okay, so this is our initial weighted vertex cover. And then we need to find out all the tight edges. Okay. Okay. So the first tight edge is between x1 and y3. And the second one is between x2 and y4. And then x3 and y5. And then x4 and y3. And finally, x5 and y4. Okay. So this is our tight edge. Okay. Okay, and then we have to find the maximum matching on this tight graph. Okay, so I think it's easy to see that. Sorry. So these 3 edges, they form a maximum matching for GT. And clearly, this is not a perfect matching because there are 2 unsaturated vertices in X. Okay, so we know that we have to modify the vertex weight. Okay, so then we need to identify all the vertices in S. Okay, so initially, we include all the unsaturated vertices, okay? X4 and X5. So we can start from these 2 unsaturated vertices going down. So Y3 and y4, they are in T. And then we use the edges in the matching to go up. So we have 2 more vertices in S, okay? And that's it, okay? So we have 4 vertices in S and 2 vertices in T. Okay. And our mission is to find some new tight edge between S and y minus T, okay? So let me highlight these edges. Okay. So the edges in these red boxes are like our goal, okay, our target. We want to make at least one of them tight. Okay. Okay, so next we're going to subtract epsilon from S and add epsilon to T. Okay. And we need to figure out what is this epsilon. And according to our previous discussion, this epsilon should be like the minimum gap for these edges in the red boxes. Okay. So for example, for this edge 4, the gap is 2 because 6 plus 0 minus 4. So we get 2 as the gap. And the gap here is 5, 3. Okay, so the gap here is 2, 7, and 1. So so far the minimum gap is 1. Okay, and in fact this edge has the minimum gap. Okay. So epsilon is 1. So we're going to subtract 1 from S and add 1 to T. So after the modification, we can add one more tight edge between x2 and y5. Okay. So this blue edge is the new tight edge that we just created. Okay, so now we have a new tight graph, and we want to find the maximum matching. And since now we already have this matching, we can only focus on the augmenting path. Okay, and so for this GT. Actually, the maximum matching still has only 3 edges. But this time we can expand S and T because from this S, we can go down to reach Y5. So Y5 now is also in T. Okay? And T, again, this is saturated, so we can use the edge in the matching to go up. So this one is also in S, okay? So even if we have a new tight graph, we still cannot find a perfect matching. In fact, in this case, we cannot even find a larger matching, okay? But anyway, we have a new set of S and T. Okay. Okay, so our goal again is to find some new tight edge. But this time, since we have new S and new T, we have a new target. Okay. So this red box, they highlight the edges between S and Y minus T. So again, we need to find a minimum gap. And this time, you can see that for this edge, it has a gap of 1. Similarly here, we have a gap of 1, a gap of 1 here, and a gap of 1 here. So we have lots of edges that can become tight simultaneously because they all have the smallest gap, 1. Okay. So minimum gap is 1. So we're going to find a new weighted verse cover. Okay, so we just add 1 to all the verse weight in T and subtract 1 from all the verse weight in S. Okay. And now we have, I think, 4 tight edge. Okay. So this becomes tight, this becomes tight, this, and this. Okay. So now we have 4 new tight edges that can be added to GT. Okay, so the first one is between X1 and Y1, and X2 and Y1, and X4 and Y2, and finally X5 and Y2. Okay. So actually now we have enough edges to create a perfect matching. Okay. So I think yeah, you can just run the algorithm that we've done for maximum matching. Anyway, I'm going to just give you the result. Okay. So this is a perfect matching. Okay. Okay. Okay, so let's double check. Okay, so the total weight of the matching Okay, so this is 31. And the total weight of the vertex weight so once again 31. Okay, and I think it's very easy to check that this is a valid weighted vertex cover because it can cover every edge. Okay, so for example, let's check all the edges in the matching. So for this one, edge weight 6, and the total weight of the two endpoints 6, so it is tight. Similarly, this is tight, and this 8 is tight because 8 is equal to 7 plus 1. 4 is tight, and 8 is tight because 6 plus 2 is equal to 8. Okay. So this is a perfect matching where all the edges are tight. Okay. So, yeah. So this is the maximum weighted matching according to our previous analysis. 好，所以到这边有问题吗？所以基本上我们这边会有的时候你会看到我们会需要 update 那个 weighted vertex cover 不止一次 ，OK？ 那因为有可能你 update 一次之后，它一样没有办法找到 perfect matching，OK？ 所以你就要不断的加边进去。那每一次你加一个边进去，因为你一定是介于 S 到 Y 减 T， 所以你一定可以去延伸你的这个 T。那你的 T 改变之后，你就有机会去做出新的 weighted vertex cover。OK， 好，所以我不知道到这边有没有。OK， 你说 S 为什么要每一个都要扣掉 epsilon 吗 ？OK， 就这一步嘛。OK， 所以 S 每一个要扣掉的原因是因为我们在找更大的 matching 的时候，我们会用 augmenting path， 对吧？那如果你要 augmenting path， 你就会用那些过去的介于 S 到 T 的那些边。所以我会希望过去介于 S 到 T 的，它一样会是 tight。因为如果它不是 tight 的，我就不能用。
照你刚刚那个例子，
对。
如果只动你可以，比如说这样子好了，
对。
这样的话，比如说你看最右边的 S，
最右边这个。
所以它可以1、2、3、4。
哎，对，它可以走4步，对。
对，1、2、3、4，然后看最右边第二个 S。
对。
是1、2。
对。对。
这样就2条。
对，这样就2条。
以这个分析，就你接下来会，比如说做几个动作，然后找出一条真正的 augmenting path。那这样的话，你只会动，比如说你只会动最右边的 S 那一条。那这样的话，不是也可以，就是说我只加最右边那一条，这样一样不会动到右边第二个 S 啊，就是这个 B， 不用到这个这样的话，它还是会维持它是那个 tight edge。也可以，它不用全部减，我的意思是这样，它不一定要全部减，照这个逻辑来看，因为你的全部减只是想要为了让它一样维持太长，那一样可以靠。那这样的话，如果只减某一部分，就是那条 updated， 这样的话不是也是可以让它维持太长，因为原本就没动。 不会出问题，可是不剪。
对，他说能不能不要？
不剪的话，问题如果不剪的话，我知道剪完不会有问题，但如果不剪，就是不是全部剪。
我是觉得可能也是可以，但是我现在不是很确定。呃，
还要去回溯那个边，然后去决定哪些点要剪，哪些点不剪。就是你干脆全部一次剪比较快，不然你还要回去回溯哪些点要剪，哪些点不剪。
主要是因为老师刚刚判断它是 maximum 的时候，它是用就是 row 还有 column 要是刚好可以 type，然后它就
对
跑出来了，所以可以直接画出那样的结果。可是如果今天不是这个做法，就是不是全部 S 都剪，不是全部 T 都剪的话，那它的做法还是一样的，就像老师最后一页那样子，就直接。
譬如说，我不确定你的意思是这样子。就如果我们回到这边好了，你的言下之意就是代表我其实我可以有点像是任选 S 到 Y 减 T 的边，让它变成 tight。因为我只需要去回溯，譬如说我们刚刚是让这个变 tight，我也可以试着让这个变成 tight。
不是，我的意思不是这样，我的意思是说，
因为你的言下之意就是我如果让这个 tight，我只要让它在它延伸到它的那个，让它变成。
他的意思是说，就是因为你原本的那个可能会有2条那个可以延伸的扩展路径。
对，有可能。
他的意思是说，假设你现在选的是其中某一条
对
的扩展路径的话，另外一条的那个点其实可以不用做加减太少。
对。
对，他的意思是这样。
OK，我就 maybe 我可以给另外一个想法，就是多减的好处是什么？就是我们到时候的目标一定是希望这个 total vertex weight 是要越小越好，所以你少减的话，就反而让它有点像是它会需要更多个回合，因为我多减的话，我就可以让这个 total 的 vertex weight 下降的比较快，我下降的比较快，就越容易确保说它跟 matching 的 total weight 是一样的。对，所以我觉得应该是可以但是可能会影响时间复杂度。对。好 ，OK。OK， 还有其他问题吗？
看最后一页。
OK 吗？所以你 OK 吗 ？OK。Okay, so so next we're going to consider like 2 new problems, but these 2 new problems they have a similar relationship between the relationship between matching and vertex cover. Okay. Okay. So previously we considered matching, and matching is just a set of edges that do not touch each other. Okay, so it's like these edges are independent in the sense that they do not touch each other. Okay, but for independent set, this is not an edge set; it is a vertex set. Okay, And by independent, I mean this for any two vertices in this independent set, they are not adjacent. Okay. Okay, so for example, these four vertices form an independent set, okay? Because for any two of them, they are not adjacent. Okay. Okay, so this is an independent set. And so the definition is that for any two vertices in this set, they are not adjacent. Okay. Okay, so there's no edge between any two vertices in the independent set. Okay, so for independent set, it's difficult to find, to maximize the size. Okay, just like mentioned. Okay, so we're going to consider the maximum independent set problem. Okay, where we want to find the largest independent set. So for general graph, finding the largest independent set is NP hard. Okay. Okay. But for this course, we're going to, again, focus on bipartite graphs. And it turns out that for bipartite graphs, there's an efficient way to find the maximum independent set, okay? And the algorithm is related to vertex cover and maximum matching, okay? So that's why I want to discuss independent set here. All right, so now what is edge cover? So edge cover is similar to vertex cover, where we want to cover some sets, okay? For vertex cover, we want to cover all the edges using vertices, okay? So we want to pick vertices to cover all the edges. So that's vertex cover. But for edge cover, we will pick edges to cover all the vertices, okay? Okay, so for example, this is an edge cover. Why? Because it can cover every vertex in the graph. Okay. So it can cover, for every edge, it can cover its two endpoints, okay? So for an edge cover, it means for every vertex V, you can find some edge in this edge cover such that this edge, incident to the vertex. Okay. Anyway, visually, it's just like we can choose edges that can cover all the vertices. Okay. And for a graph to have edge cover, we have to make sure that there's no isolated vertex. Okay. So recall that an isolated vertex is a vertex without any neighbors. So if a vertex has no neighbors, then we cannot have an edge cover. Okay. So we're going to assume no isolated vertex. Okay. And also, the reason that we consider edge cover is that it provides an upper bound for independent set. Okay, so this relationship between independent set and edge cover is similar to that of matching and vertex cover. So next, let's consider these two sets. Okay, so we have an independent set that's called I. Okay. Okay, and also we have an edge cover. So this edge cover is denoted by CE. Okay. So there's a very simple relationship between these two sets. That is, the size of this edge cover is at least the size of the independent set. Okay, so can you see why?所以这里跟那个 matching 跟 vertex cover 很像，就是任何一个 matching 的大小都不会超过任何一个 vertex cover 的大小。OK， 只是这边有点 edge 跟 vertex 颠倒，就是 matching 是要找有点像是不相关的 edge， 那这边是要 independent set 是要找不相关的 vertices， 然后我们 vertex cover 是要用 vertex cover edge。然后这边是用 edge cover vertex， 所以有点像是就是角色都有点对调，但是这边我们一样有这个关系 ，OK， 所以有人可以看出来为什么吗？好像有一点不是很精准的地方，对，所以任何一个 independent set， 你随便画一个 independent set， 你再随便画一个 edge cover， 那个 edge cover 大小一定会比那个 independent set 更大，或相等，也有可能会相等。如果是我们前面这个例子的话。这个 independent set 大小是4，那 edge cover 的大小是4，刚好这个例子刚好是一样 ，OK。idea 跟那个 matching 跟 vertex cover 的关系是一模一样，它的 argument 是基本上是一模一样。所以我们稍微回顾一下 matching 跟 vertex cover 的关系。我们那时候怎么说 matching 的大小一定不可能超过 vertex cover？ 就是因为 matching 的边都不会碰在一起，所以如果你光要 cover matching 的边，你如果有3个 matching 的边，你就至少要3个点才可以 cover 它们。OK， 因为你不可能用一个 vertex 就 cover 多个 matching 的边。OK， 所以这边也是一模一样的道理。OK， 所以 idea 很简单，就是如果你是 independent set， 比如说像这个 independent set， 这有4个点，这每一个点它都一定会需要单独一个 edge 去 cover， 你不可能用一个 edge 就 cover 2个 vertex 在 independent set 里面，因为如果你可以用一个 edge cover 2个，那就代表这个根本就不会是 independent set。OK， 所以基本上是一模一样的道理。OK。Okay, so this is proof. Okay, so we cannot cover multiple verses in an independent set with just one edge. Okay, so if you have 2 verses in your independent set, you have to use at least 2 edges. Okay. So if you consider the proof for matching and vertex cover, then we just need to change these vertices to edges. And this I, change it to M. So we cannot cover 2 edges in a matching using one, sorry, this should be changed to vertex. Okay. So basically the same idea, okay? So I think the root cause is that we consider this independent idea. So if the set is an independent elements, this means you cannot cover multiple elements at the same time, okay? So yeah, that's I think the basic reason. Okay. Okay, so when we discuss matching and vertex cover, we show that sometimes the largest matching has the same size as the smallest vertex cover, at least in the case of bipolar graphs. Okay, but for non-bipolar graphs, the largest matching can be less than the size can be less than the size of the smallest vertex cover. So we have this similar relationship between independent set and edge cover here. Okay, so let's consider an edge cover. Sorry, an arc cycle. Okay, so what is the maximum independent set? No, I think at most 2. Independent set. Okay, so after you choose this one, yeah, you can choose at most one more vertex. Okay. So I use I star to denote the maximum independent set. Okay. And CE star is the minimum edge cover. Okay. So what is the minimum edge cover? we have to use at least three edges because one edge covers 2 vertices. Okay, but we have 5 here, so we have to use at least 3. Okay. So in this case, the size of I star is strictly less than the size of the minimum edge cover. Okay. For non-bipolar graph. Okay. All right, so I guess you can see where we're going. So next we're going to consider bipolar graphs. Okay. So it turns out that for bipolar graphs, they are the same. Okay. So that's our second goal today. Okay. So we're going to show that for bipolar graphs, the maximum independent set has the same size as the minimum edge cover. Okay. And along the proof, we actually will give you an algorithm to find the maximum independent set and the minimum edge cover. Okay. Okay. Because now we have considered 4 different sets. Let's draw these 4 sets in one graph. Okay, so first, the matching. So I'm going to use M star to denote the maximum matching. Okay, so for this one, all right, so this is maximum matching. We also have the edge cover. And recall that to find the edge cover, we consider this set, okay? T union X minus S, okay? So once again, let's identify S and T. So initially, we only have this unsaturated vertex as S. So we go down to reach this vertex. So this one is in T, and then we can go up. So this is in S. Okay. So what is the minimum edge cover would be the minimum vertex cover would be T union X minus S. Okay. And what is I star? Well, we haven't developed an algorithm here, but I think visually this is I star, okay? Okay? And finally, the edge cover. Sorry. Maximum independent set. Sorry. And we know that this is the largest or maximum independent set, and this is the smallest or minimum edge cover because they all have the same size. Okay? So we have 4 vertices in independent set and 4 edges in minimum edge cover. So these 2 quantities are the same, which implies that they are actually the best. Okay? So next we're going to, well, take a break, and when we come back, we're going to consider the relationship between these 4 sets. All right, so let's take a break.
对，我想要用不那么 A 这样的也是 A。
对，他是这样跟我讲。
我操！
有些点我变的时候会就加强 A 就好，因为 A 就好有个点我一定不就是 A 就好的时候在这里，就是没有任何没有空间可以考虑，A 就好本身就是没有 flexible。这个我们要讨论的是在 A 就好要大家是想要实现的事情，要当或者是在 A 就好一件可是或者是 A 就好的话，就是你这种 A 就好做都反过来，因为为了要顾及 flexible。所以你不能像我这个创业嘛，为什么？因为它可能会需要一个需要有变动，然后那个我觉得用这个变动这个信息啊。然后就他说照你的做就真的要，他不想，他是这一次才会不死。我是没有叫他变那个明星有一张信息号码，我是叫他怎么跟我变那个敏捷症就很好，所以我没有选择全力我们去，我还没有。因为如果像刚刚这样子确实就给他去学校吧，也是自己可能在做对，我不知道，我觉得这个确实按着去搞。没有。靠他的几个亿，那个有几兆钱。
All right, okay. So next we're going to consider their relationships, okay? So, but I think at least from this example, we can have some guess, okay? So for example, what do you think is the relationship between the minimum vertex cover and maximum independent set? That is this red and blue set. So at least from this example, we can see that their union is simply the vertex set, okay? Okay, so we have the maximum independent set and the minimum vertex cover. Okay, and their union is just the vertex set. Okay. So it turns out that this is true, okay? So the union will be the vertex set, but we're going to prove some more general result. So the first result is that So here I is just any independent set. Okay. So if you take any independent set and remove this independent set from the graph, then the remaining vertices will form a vertex cover. Okay. And the second claim is that if you have any vertex cover, so this CV is any vertex cover. Okay. You take any vertex cover, remove it from the graph, then the remaining vertices will form an independent set. Okay. So we'll first prove these two claims, and then we'll go back to come back to this example. Okay. So we have the vertex set V and an independent set I. So I want to show that the remaining vertices form a vertex cover. Okay. So why? 所以可以看出来为什么吗？所以你有一个 independent set， 随便一个 independent set，OK， 然后你把它删掉，那删掉之后，剩下那些一定就会是一个 vertex cover。比如说在这边，至少在这边也是一样，你把这4个点删掉，它就会是一个 vertex cover。嗯哼。嗯哼。
所以呢，你不会有没有覆盖到的点。
Yeah. So, yeah， 所以基本上这个 idea 就差不多是这样。那另外一个，你譬如说可以用视觉上，你可以这样想，就是如果我们看反证法，就是红色这个，如果它不是 vertex cover， 那会发生什么事？如果它不是 vertex cover， 就代表它一定有一个 edge 没有被 cover， 没有被 cover 的 edge 一定会出现在哪里？ So this V set minus I is not a vertex cover, which means some edge in the graph is not covered by this red set. Okay? So it must be the case that this edge, so some edge is not covered So this edge must reside within this set I. Why? Because if some endpoint like U is in this red set, then we can cover this edge. Okay, or V is in this set, then we can cover this edge. So the only case that we cannot cover this edge UV is when U and V is not in this red set. Therefore, it is in this set I. Okay, and that's a contradiction because we said that this I is an independent set. So since this is an independent set, you cannot find any edge connecting any two vertices in I. Okay, so that's a contradiction. So yeah, that's it. So if you remove any independent set from the vertex set, you get a vertex cover. Okay. And next, let's remove any vertex cover. And we'll show that the result is an independent set. Okay. Okay, so the picture looks similar to the previous one. This time we consider this blue set, where we take out this vertex cover from the graph, okay? And we want to show that this is an independent set. Yeah, very similar reason, okay? So if this is not an independent set, this means we have an edge U, V in this blue set. But then there's a contradiction because you claim that CV is a vertex cover, but you cannot cover this UV because U is not in CV and V is not in CV. So that's a contradiction, okay? Okay. All right, okay. So proofs are quite easy, okay? All right, so now we have these two claims. So for any independent set, you can remove it, and you get an vertex cover. So we can replace this any independent set with the maximum independent set. Okay, so this means okay. So if we remove the maximum independent set from the graph, we get a vertex cover. So what does this tell you? So let's consider the size. Okay, so this is some vertex cover. And this is the minimum vertex cover. So since this is the minimum vertex cover, any vertex cover is at least as large as the minimum vertex cover. And what is the size of V set minus I star? Well, it is just n minus the size of the maximum independent set. Okay. All right, so the result is this. Okay, so we get an inequality between the size of the maximum independent set and the size of the minimum vertex cover. All right, so this is the first inequality. So next, let's consider the second property. So this says if you remove any vertex cover from the graph, you get an independent set. So this time, we're going to replace this any vertex cover with the minimum vertex cover. Okay. So this is the size of some independent set, and this is the size of the maximum independent set. Okay. So the size of the maximum independent set was certainly larger than or equal to the size of any independent set. And this is equal to n minus the size of the minimum vertex cover. Okay. So the result is that m minus the size of CV star is less than or equal to I star. Okay, so we can rearrange this term. So combining these two inequalities, we get n is equal to the sum of these two, the sum of these two sets size. Okay, so this is the first relationship between these four sets. Okay. And recall that our goal is to show that if we consider bipartite graphs, okay? So if we consider bipartite graphs, then the size of the independent set, maximum independent set is equal to the size of the minimum edge cover. Okay. And actually for this proof, for these two proofs, we haven't used any properties about bipartite graphs. So these two properties also hold for general graph. Okay, so in this picture, there's no bipartite graph. Okay, we didn't divide sets into x and y. Okay. Okay. And next, So next we're going to consider the relationship between these two edge sets, the green edge set and the yellow edge set, okay? But this time we cannot take their union, okay, because their union cannot be like the edge set, the entire edge set, no, okay? So we can see that they have some common edges, okay? But if you consider their total size, okay? So the yellow edge has two yellow edges and 4 green edges. So in total we have 6 edges, okay? And 6, once again, is equal to the number of vertices, okay? So we can guess if we have the maximum matching and the minimum edge cover and consider their sum, by sum I mean the total size, then the total size will be, once again, n. Okay. In other words, since both sum, they equal n, so these two sums, they are the same. Okay? So I star plus CV star is equal to M star plus C star. Okay? But recall that we also know that the size of the matching, maximum matching, equals the size of the minimum edge cover, minimum vertex cover. Okay? So if these two sums, they are the same, and M star is equal to CV star. So we can cancel out these two terms. And the result would be I star has the same size as C star. Okay. So this finishes our goal, okay? Yeah, OK。第二个指的是我们等一下会来看这两个 H set 它们的关系，就是 matching 的大小，就是 M star 的大小，就是这里的黄色的边，还有minimum edge cover 就是绿色的这个边，我们去看它们的关系。那这边的关系跟上面这个有点像，就是我们去看它们的大小的总和，它们大小总和一样会是 n。OK， 所以我刚刚说的事情是因为这两个总和都会是 n， 所以这两个总和就会是一样。如果这两个总和是一样，然后我们之前有讲，如果是 biparallel graph 的时候 ，M star 跟 CV star 它们是一样的，所以你就可以把这两个消掉 ，OK， 所以你就可以得到说这两个 I star 跟 C star 它们的大小是一样的 ，OK。那但是这个因为我们第3步就有用到 biparallel graphs， 所以这个只有在 biparallel graphs 的时候才会 work，OK。因为如果是不是 biparallel graph， 那上面这个例子就已经告诉我们，就是它们的大小有可能不一样。好，所以我们接下来就是要看这个 maximum matching 跟 edge cover 的关系。Okay, so the green edges is the edge cover. So in fact, the minimum edge cover. And the yellow edges are the maximum matching. Okay. So not like unlike the relationship between independent set and vertex cover, we cannot just remove edges, okay? Because if you remove, for example, remove these 2 yellow edges, well, you get 1 extra edge here. And if you remove these green edges, again, you have this 1 extra edge. So we cannot just remove edges, okay? So let's first construct an edge cover from matching. Okay. So this is our first goal. Okay, we're going to construct an edge cover whose size is m star. Okay. And then we're going to do the other direction. It is matching. So there's sorry, not m star, n minus m star. So for the first part, you can think of this as given a matching, a maximum matching, you need to create an edge cover based on that matching. And the edge cover must have a size of m minus the size of the matching. Okay, so this is the first goal. And the second goal is that you are given an edge cover, in fact, minimum edge cover, and you have to build a matching. And the matching has the size m minus the size of the minimum edge cover. Okay, so let's do the first part first. Okay. So this time we have, we have a matching, right? Okay, and then based on this matching, we have to create an edge cover. Okay. Now, for every to have an edge cover, you need to cover every vertex. Okay, so for example, if this should be m star. Sorry. Okay. Sorry. Okay. So if this matching is a perfect matching, then we can just take the matching, right? Because it saturates all the vertices, which means it covers all the vertices. Okay. So let's check. Let's say if m star is perfect, then m star is a valid edge cover of size. Well, what is the size? Okay. The size can be m star. But actually, m star is equal to, since it is a perfect matching, implies that the size must be n divided by 2. Therefore, it equals m minus m star. Okay. So this is our target. Okay. So we want to have an edge cover of size m minus m star. So if the matching is perfect, and we're done, okay? So how about the case where the matching is not perfect, like this one? So for this matching, there are two unsaturated vertices, okay? So a very simple way to create an edge cover is that for every unsaturated vertex, you just, we have to cover this. So we add one of its incident edge, okay? Okay. And for this one, we add this edge. So if M is not perfect, or M star, sorry, for every unsaturated vertex, we choose one of its incident edge. Okay. And we also take all the edges from the matching, okay? So initially we take all the edges from M star, and then for every unsaturated vertex, we pick one edge that is incident to it to cover the vertex, okay? So this is a very simple way to create an edge cover, okay? All right, now, so the problem is, what is the size, okay? So the size is just the size of the matching, because we take all the edges from the matching, plus the number of unsaturated vertices. Okay. So now, what is the number of unsaturated vertices? Well, it is just M minus the number of saturated vertices. And what is the number of saturated vertices? It is just twice the size of M star. Okay, so the result, M minus M star. Okay. All right, so this is how we create an edge cover from a matching. So actually for this proof, we didn't use any properties about maximum matching, so we can change this M star to any matching, okay? So, yeah.什么不一定？ Okay. Okay, next we're going to create a matching. From a minimum edge cover. Okay, so this time we have the minimum edge cover, okay, and we want to create a matching, okay. Okay, so for this part, we really need the property of minimum edge cover, okay. Okay, so next first I'm going to consider a new graph. So this new graph consists of all the vertices and all the edges in the minimum edge cover. Okay, so for example, for this graph and this minimum edge cover, this is H. Okay. So very simple. We only consider the edges in the minimum edge cover. Okay. If it is not in the edge cover, we will not include it in H. So the claim that I'm going to make is that look at every component of H. It will be a star. So what is a star? So a star looks like this, okay? So it's like a tree, and the depth is 1, okay? Or the height is 1. Okay?对，所以这边我们第一个要做的事情是，我们要去看一下这个 minimum edge cover 它这些 edge 建出来的 graph。那我这边的 claim 是这些这个新的这个 graph H， 就是我只考虑 edge cover 里面的 H。如果你去看它每一个 component， 它都会是一个 star 就是有点像 tree， 然后这个 tree 的深度就是1 ，OK。所以举例来讲，什么不是 star？ 比如说，这个 path 它就不是 star，OK，、然后三角形也不会是 star， 那当然这个也不会是 star，OK，、这就不是 star。OK， 所以有人可以看得出来为什么吗？所以这个也不会很难，这个也蛮简单的。所以这边关键是我们看的是最小的 edge cover。那 edge cover 是什么 ？edge cover 就会是你要 cover 所有的 vertex，OK，、然后你要用最少的边。所以举例来讲，如果你要 cover 所有的 vertex， 你要用最少的边，你有没有可能你选出来的边里面会有三角形？不可能，为什么？OK， 但是这边它这个 claim 并不一定是 apply 在 bipolar graph， 它 general graph 都可以。那比如说四边形啊，所以它有没有可能只有一个四边形？没错，所以你一定要说它一样可以 cover 所有的 vertex。所以这个像这个 path 也是一样，这个为什么它不会是最小的 edge cover？ 因为你可以移掉中间这个 ，OK， 所以这个它。这个每一个 component 一定会是一个 star，OK？、所以这个 path 的长度一定不可能大于等于3，因为大于等于3，你一定可以移掉某一个，然后你也不可能有三角形。所以基本上这就排除所有的可能，像这个它就是有一个 path 是3的，所以这个一看就知道不可能。啊，这个是三角形 ，OK， 所以三角形也不可能，因为你可以移掉随便一个。 Okay, now we're ready to create this matching. Okay, so now we know every component of H is a star. Okay, so it looks like this. Okay, so this is all the edges in the minimum edge cover. So now we have to build a matching. Okay, so how to build a matching? So it seems like there's only one reasonable way of doing so. That is, for every star, we pick an edge. That's it. Okay, we cannot do any better. Okay. So for any star, pick an edge, and that's it. So back to the previous example. So here we have two stars. So for every star, we pick one edge, and we get a matching. Okay. So clearly, this gives you a matching. Okay, because edges that we pick are from different components, so they cannot be adjacent. So now the remaining question is, what is the size? Okay. Well, the size is just the number of stars. Okay, and what is the number of stars? We have to relate this size to the number of edges. Okay. Well, star, to count the star, you can count like the number of loops. And to count the loops, you can just count m minus the number of leaves. Right? Because, well, it is a star, so if it is not a loop, then it is a leaf. Okay. And what is the number of leaves? Well, the number of leaves is just the number of edges. Okay, so the size is m minus c star. Okay, so let's summarize the two properties. Okay. So we have an edge cover of size m minus m star. So this is the size of some edge cover. So since this is some edge cover, it must be at least the size of the minimum edge cover. OK， 所以这边因为第一个告诉我们就是某一个 edge cover 的大小，那某一个 edge cover 它当然会比那个最小的 edge cover 不可能比它更小，所以一定是大于等于。And from the second property, we can get that m minus the size of c star. So this is the size of some matching. So if it is the size of some matching, it cannot be greater than the size of the largest matching. Okay? So rearrange terms, and we get m is equal to their total size. Okay. And this is the second equation here, okay? All right, so yeah, after we have these three equations, we get that for bipolar graphs, the size of the maximum independent set is equal to the size of the minimum edge cover. And also, we have an algorithm for computing these four sets. So we already know how to compute M star and CV star. And now we also know how to compute I star. That is, we take out all the vertices from CV star, right? And it will give us I star, okay? So remove CV star, and we get I star. And how to get the minimum edge cover? Well, this, okay? Start from the maximum matching, and for every unsaturated vertex, you pick one edge, and that's it. Okay, so this gives you CE star. Okay. Okay, so 有问题吗？所以我们今天主要就是看这四个 set。我们下礼拜，因为我们主要目前都是看 bipolar graph， 那这原因是因为在 general graph 的时候，我刚刚说了 independent set 或 vertex cover 它们其实只是 NP-hard，OK，所以我们下礼拜我们会看 vertex cover 在 general graph 上面，我们没办法拿到最佳解，因为拿到最佳解要至少目前没有人知道怎么在 polynomial time， 所以我们下礼拜会看的是怎么在 polynomial time 找到一个蛮接近最佳解的 vertex cover，OK，我们会考虑有 weight 跟没有 weight 的版本。然后我不知道大家会不会很好奇，就是我们当初在看 matching 的时候，我们说 upper bound， 然后我们的 upper bound 是很神奇的是，要去看 vertex cover。从 matching 到 vertex cover 这逻辑的过程不是很清楚，就突然间天外飞来一笔，我就跟大家讲，你就考虑 vertex cover，OK。然后这边刚刚也是一样，就是我们刚刚本来要考虑 independent set， 然后我说，如果你要考虑 independent set， 你要考虑 edge cover， 那就是一样，就是突然间感觉考虑一个毫不相关的问题，所以我们也会看到底从一个问题出发，我们要怎么得到另外一个那个给你 upper bound 或 lower bound 的那个问题，所以事实上这有一个有系统化的转换，叫做 primordial 的 transformation， 所以我们下礼拜也会去看这个转换。OK， 好，所以如果大家没问题的话，我们就上到这里。